So the next theorem is a very interesting theorem. So if we have Fn converges to F in distribution, then there exists there exists a random variable yn, which has the distribution Fn, such that yn converges to y almost surely, where y has a distribution of f. So this is so which tells us that if we have this convergence in distribution, we can always construct the sequence of random variables and the limiting random variables such that this sequence converges to that limiting random variable almost surely. So it becomes stronger. So a very weak convergence in distribution also indicates there exist random variables or measurable functions that will converge almost surely, which is the strongest convergence. Right, so that's very interesting, and the idea is I won't prove it. It's also too much analytical, stuff. But the idea is that we define the random variable yn to be the inverse of fn. So we're gonna find the inverse, but the inverse may not be one-on-one. So we take the soup of the y, which makes the fny is less than x, and that fn will be our random variable, and y is a similar idea, and it can be proved that this yn converges to y for almost surely, which means only a countable number of x, which is the discontinuous points of fn, that is doesn't converge, but that has a probability that set of points has a probability measure 0. So that's how we prove for existence of such random variables. And then the next one is very important one, the Portmanteau Lemmas. So what is Portmanteau Lemmas? It's a list of lemmas, equivalent lemmas, but here I'm gonna only mention 2 of them. The first one is that if xn converges to x infinity, xn converges to x infinity in distribution, if and only if, so this converges in distribution if and only if every bounded continuous function we have the convergence in expected value. An equivalent statement of this one is that we don't need every bounded continuous function. We just need a continuous. We just need a bounded, but not always continuous, but it's Lipschitz continuous, a special continuous function, and we have the expected value converge as well, and this is also equivalent. So if we can find we can prove that every Lipschitz function that is converged in expected value, we can prove the xn converges to x infinity. Same around. So the Lipschitz continuous function is a special continuous function, which states that if f is a Lipschitz function, then there exists a case such that the absolute value of fx minus fy is less than or equal to k times absolute value of xy. So basically, what it says that the value of fx minus fy does not go beyond the slope of x, the slope of k. So it's bounded on the x, the 2 sides of the x. It cannot go to the top section of the x. It cannot go to the lower section of the x. So that's that's the Lipschitz continuous function. So a Lipschitz continuous function is definitely a continuous function, right? Because we can, we can let x minus y to be less than some 1 over k, and that less than epsilon over k, and so epsilon over fx minus fy will be less than epsilon. So Lipschitz continuous is continuous functions. The proof is also analytical, but worth looking at. First, you see I have a graph here. So this is the function we constructed, and we're going to use that function to prove the two lemmas. The first thing, let's see what is this function. So we're going to use the theorem here. So if converging distribution, then we can construct yn yn converges to y almost surely. Then so by the theorem above, there exists yn converges to y infinity almost surely, holding the same distribution of x and x and infinity. And since g is a continuous function, so g is a continuous function, either this one or Lipschitz continuous, we have this converges in almost surely. Since g is bounded by the bounded convergence theorem, we have that the expected value converges. And since xn and yn has the same distribution, we have the expected value of xn equals to expected yn, expected value of x infinity equals expected value of y infinity. So the first, so that's the direction. So that's the direction we want to. That's the first direction. Given convergent distribution, we have proved that converge in expected value of bounded functions, bounded continuous functions, or bounded Lipschitz continuous functions. Now we want to prove the other direction. So we want to prove that Lipschitz continuous and convergence in expected value indicates convergence in distribution. So let's construct a continuous function, or Lipschitz continuous function. In fact, the function we constructed is both continuous and Lipschitz continuous. The function was illustrated in here. So it's a function of with two parameters x and epsilon, and the input y. So this function will be equal to 1 if y is less than x, and will be the function will be 0 if y is greater than x plus some epsilon. And then if y is between x and x plus epsilon, then this is the slope connecting 1 and 0. And that's what you see in here. So x, for example, x is phi and epsilon is phi. So x plus epsilon is here. So this point, the lower point is 0, the upper point here is 1, and that's connecting this function. And as you can see, this is actually Lipschitz continuous. The Lipschitz k is the slope here. So the function we constructed is both continuous and Lipschitz continuous, and it's bounded. It's bounded by 1. And then we know that this will converge. So let's see. So expected value of gx, which is just we're gonna split the x to be 2 sets, or one set is less than or equal to x. Three sets. One set is less than or equal to x. The other set is in the middle of this slope, and the last set is when oh, this is a little bit too small. Well, it goes beyond that slope. Okay, it's hidden here. Okay. So here, this is the slope, well, the last one is just 0, so it's not included. So, but this one is the first one is just the probability of xn less than equal to x, and the second one is the slope. Let me still a little bit to yeah, dp here. So because of that, we know that the limit of xn less than equal to x is because this is, first of all, this is a positive function, so this the last one is also positive, so we know that this one is definitely less than equal to the limit of expected value g and gxn. So let's zoom in again. And but limit of that is as we know, this goes to expected value x infinity. That's what we know by assumption, and this is less than equal to, this is something. Just look at that. Expected value of gx infinity is this function, right? Gx, but gx infinity is it's less than the probability of x infinity less than equal to x plus omega. Right, so so the expected value of gx infinity is less than or equal to probability of x. Right, so the expected value of x infinity less than equal to x plus omega is from here, right? So this is the region where we are taking expected value of, right? The probability is just of an indicator. This is just an indicator function, right? This is what we just talked about here. So this is taking an integral of this region from, so it takes a little bit larger region than the expected of a g function, the g function here, which is only taking this part and the slope. So there's a smallest, the upper corner here was not included in the expected of gx, but it's included in here. So the expected of gx infinity is less than equal to the probability of x infinity less than equal to x plus or epsilon. And when epsilon goes to 0, we have this is less than equal to this. And it's a similar idea proving the other direction. So I won't go through that details, but it's a similar idea. We're gonna have something that is similar to what we see here. So there's some typos here. I need to fix that. And that will prove the convergence in distribution. And that because this g function is both continuous and also Lipschitz continuous. In both cases, we proved the xn converges to x infinity. So that's the Portmanteau Lemmas.